Greetings and welcome, friends. Yesterday we were talking about two special types of segments within triangles of 5 that we'll end up learning about in this chapter. We learned about perpendicular bisectors, okay, which intersect at a point called the circumcenter, as shown here, I suspect. And it had some interesting properties as a result. Now it says they intersect at point G and are shown in blue. They're lying. I inverted the colors. They're the orange ones. So G, D, and GE are the perpendicular bisectors, right? They're perpendicular to the sides of the triangle. If I drew the third, oh, there is the third perpendicular bisector right there. Right there. Beep, 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 beep. All right, there we go. At GF, and they have a point of concurrency called the circumcenter, and it says find the indicated measure, Ga. And one of the interesting things about these is that the circumcenter is equidistant from A, B, and C, so that means this segment is congruent to this segment, and this would equal 11 by def of Kong. Just to show that those are in fact equidistant, I don't believe I've changed the scale of this picture. If I draw the circle here, notice that it does hit all 3 points, which is somewhat of like a visual verification that all 3 of these blue segments, which were formerly red, are in fact radii and equidistant. This circle is called a circle. It circumscribes the triangle. There you go. And also every triangle has exactly one circle that circumscribes it. Then we have this other concept about angle bisectors, which are these blue segments here. They have a common point of concurrency. That was called the incenter. And it says find the indicated measure, HP, Hewlett-Packard. Property of the incenter is that it is equidistant from the sides. Of course, we measure distance of a point to the sides of a figure perpendicularly, and therefore this is going to equal 15. And just to verificado that this is in fact the incenter and equidistant, notice I can draw a circle, which is the inscribed circle in this triangle, of which there is only one type of circle ever where it is said to be tangent to the sides. Tangential is when a line or ray or segment touches a curve at exactly 1 point, which is a pretty cool thing to consider. That's actually a calculus concept, the idea that you could end up finding the slope of the tangent line at an infinitesimally small point, right? Like at a particular location. So I could actually then, as a result, talk about the slope of the circle at these different locations. And so you could predict that the slope of the circle at K is actually 0, oddly enough. And you can then actually use slopes of zeros of curves to be able to find maximum values and minimum values. But that's just a whole bunch of random calculus that you don't need to know right now. All right, here I gave you a sketch. You're welcome. You're welcome, friends. And I would need to construct the perpendicular bisectors to find the coordinates of the circumcenter. Now, I only need 2, although all 3 of them would form be concurrent at the circumcenter. So here, if I find the middle of JK, which I could have done using the midpoint formula, I can now draw perpendicular to that. Question, what is the slope of a line perpendicular to a horizontal line? It's undefined is correct. That is correct. So this is going to be a vertical line passing through that midpoint. Ooh, lovely. Like so. This is an obtuse triangle. I'm expecting that the circumcenter will be on the outside of the triangle. Let's see. HJ, let's find the midpoint here. It's it looks like 4 square roots of 2 is the distance there. Later on, I'll show you some tricks on how to find that. The midpoint's going to be right here. You also can find the midpoint using the Ryan method. If this is down 4 over 4, cut those numbers in half. Down 2 over 2 will land you at your midpoint. So there's our midpoint. Now question, what is the slope of HJ? Down 1 over 1. Or just -1. So what's the slope of a line perpendicular to that? Yeah, it's going to be +1. So up 1 over 1. So the slope of our line is going to be the opposite reciprocal. Sometimes I call this slope 1, slope 2. The reciprocal of 1 is 1, and the opposite would be positive. So let's draw this line. That's terrible. It's just the terribleness of a drawing. There we go. That's kind of more or less hitting the corners, corner to corner. All right, there we are. So it appears as though our circumcenter is hitting at this point, which you could kind of read as at -4, 9. Now, so that's a graphical way of doing this, but I'm going to take, maybe I can do this super fast, and in like 4 minutes, I'm going to do this algebraically. All right, let me work with HJ. I'll at least show this portion. So let's see, find MP. All right, is one of the things I could do. So if I found this algebraically, the midpoint of that MP is going to be the average of the x's and the average of the y's. So -10 plus -6 over 2, and 7 plus 3 divided by 2. So the midpoint is going to be -16 over 2 and 10 over 2. And I end up getting a midpoint of -8, 5, which is the location of this point. Notice -8 up 5. That is, in fact, what I get. Now, if I want to find the equation of this perpendicular bisector, we've done that before. Find equation of perpendicular bisector. So I know that the slope of HJ I could have found algebraically as well. It's going to be y2 minus y1, 3 minus 7 over -6 minus -10. I just want to kind of like algebraically show you that what we did graphically is accomplishing the same thing. So this would be -4 over +4, so the slope is -1. So the slope of our line being perpendicular is going to be +1, which we'd already talked about. So now I've got a point and a slope for my line. If I want to find that equation, I'm going to plug it into point slope form or to slope intercept form. Either way works. So y minus y1 equals m parentheses x. Let me show you. I'll show you. We'll see. No, but if I was to do this algebraically and I didn't nicely give you a beautiful graph to work off of, this is what you'd do. So let's see. So we'd have y minus y1, so that's 5, equals m, which is 1, times parentheses x minus x1, which is -8, so that's going to be +8. So here's the equation of this blue line. We could distribute and set it in slope-intercept form if you're more comfortable with that. Add 5 to both sides. Y is going to equal x plus 13. So guys, this equation is y equals x plus 13. This equation I could have found similarly. I could have also found the equation of the perpendicular bisector for HK. This equation, does anyone know the equation for this vertical blue line? The slope is undefined, but the equation... Yeah, -4, right? So, so once I have two equations, what I can do, how can I find their intersection algebraically? Yep, it passes through the x-axis at -4. A vertical line is going to be an equation x equals a number. Horizontal lines will be y equals a number. So let's see, find the intersection of the perpendicular bisectors. This is going to be a callback to your Algebra 1 class in which you would solve a system of equations. I think we've done some, did we do some of that at some point? So if I have y equals x plus 13 and x equals -4, how do I solve that algebraically for both x and y? Substitution is a perfectly legitimate method, or the elimination method. Yeah? You guys recall any of that? So solve one of the equations for one of its variables, which was already done here, and then plug it into the other equation. So -4 plus 13, I get y equals 9. And notice I now have a combination of x and y, which is my solution -4, 9. So you can algebraically find the intersection, and notice that is graphically what I also have. So if, for instance, your coordinates were far less friendly, if your midpoints were fractions or decimals and weird things, you could accurately, exactly find the intersection using algebra in this method. So find the midpoint, find the equation of your perpendicular bisectors, and then use a system of equations to find the common point of intersection. Yeah, I think so. All right. Let's see. If this is the in-center, use the given information to find the indicated measure. Wait a minute. Wait, what? Wait a minute. Guys, these instructions do not relate to this. Garbage, Mr. Waddy. Man, swing and a miss. It says P is the circumcenter, okay, of triangle XYZ. Use the given information to find PZ. So if PX is 3x plus 2, and PY is 4y minus 8, we know that because it's the circumcenter, it will be equidistant from the endpoints. We also know that PZ is going to be congruent to those. Because these both are congruent, their measures are equal by def of Kong. So I could say 4y minus 8 equals 3x plus 2. They didn't ask for all the explanation, but I figure I might as well. Wait a minute. That's an... Why did I write y? Guys, you gotta catch me on these things, man. You gotta catch me on these things. So yeah, I figured I'd repeat the explanations as to why these are true, so then when it comes to proofs or whatevers, we can be familiar with the reasons why it's true and not just be like, I don't know, it looks true. Right? Because it's good to believe things that are true. That's good. Add 8 to both sides. X equals 10. Now, they want to find the value of PZ. PZ is equal to XP, which is equal to 3 times x plus 2. But if I plug in 10, I could get 30 plus 2, 32. Right? For PZ. You like it? You guys love the algebra. I know it. All right, last thing. Let's see if I can do a construction. You guys got your multi-tools, which, by the way, Les Stroud never goes out into the wild without taking one of those compass protractor gizmos. It's true. He says it's the #1 survival tool. So it says find the in-center. The in-center is going to be the intersection of the angle bisectors. Whoa, slow there. So let's see if I can create an angle bisector. So first thing I've got to create is an arbitrary arc from one of those points. And then using the intersection, I will scale this up so it's at least passing, because I'm expecting a midpoint here. It's got to go more than halfway past it, right? So here's one arc and then the same radius on the t'other side. And if I draw the line through those, Ra-ba-ba-ba-doo, ra-ba-dee-ba-da. Like this. This is an angle bisector, all right? So these two angles are congruent. Actually, one of you guys might even be able to tell me what that angle measure is. It looks like it's going to be a decimal. 67.5 is the claim. All right, let's find another one. I'll divvy up this. I don't know. What do you think? Maybe the 20-degree one. All right, let's bisect an angle once more. Oh, you were able to... That's good to know. And even though I changed the scale, angle measure, we all agree, maintains congruence when you dilate an object, right? Just the side lengths of the triangle that I changed. And drawing the triangles. Angle bisector. I'm only going to draw two here for you today. Also, when you make an angle bisector, notice you actually, with the vertex of the triangle, you end up with 3 points. This one, this arc intersection, and that arc intersection over there. So you've got more than you need to work with. So this, what's the name of this point? No. The incenter. And the claim is that if I measured perpendicular to the 3 sides of the triangle, that those distances would be the same. It looks like I might have had a little bit of error. But that's what we get. All right, so this circle is the inscribed circle and is, right, have a center at the incenter, which is found by constructing the angle bisectors, and it's a beautiful thing. Thanks for watching, internet friends. Bye-bye.